Hello everyone. My name is Mania and I am a PhD student at Northeastern. Today I'm talking about my thesis project, Workflow Motif, an abstraction for building distributed systems. This is a joint work with my advisors at Northeastern and Tufts and our collaborators at Boston University, Red Hat, and State Street. I want to start the talk with contrasting how we build these complex distributed systems versus how we debug them. Today, distributed systems are amazingly large scale and complex. And the way we are building these complex distributed systems by leveraging abstractions. Abstractions are the fundamental building blocks of the distributed systems that let developers build complex distributed applications. What they do, they mitigate the amount of complexity that developers has to deal with. They allow developers to build these really complex distributed applications from simpler building blocks that provide specific functionality while hiding the details of those building blocks. Examples of abstractions include APIs that allows distributed applications to build out of other distributed applications, such as leader election in consensus protocols or libraries which provide commonly used code. Another abstraction is the clean separation of different layers in data centers. That, for example, allows for separate stack layers of networking, virtualization, and application. This allows developers to write code for upper layer applications while they don't care about what is happening underneath. In contrast, when we debug distributed systems, typically we use less abstraction. We use less sophisticated abstraction. In fact, the de facto approach to debug these systems is to use no abstraction. We use user-like, or we might look at the raw logs, such as these graphs that I've shown here, and which shows the activities in the system, and shows how the system is processed by how the requests are processed by the distributed system. This difference in sophisticated abstraction we have in building distributed systems versus no abstractions when debugging them is a huge problem. What we have observed in the traces show that there are repetitive patterns within and across many traces, and these patterns are repetitive building blocks of how distributed systems behave. We believe that understanding the performance of these patterns, how they differ from engineers' perspectives, and how they combine to process request workflow will inform a wide range of diagnosis tasks. In this work, we are exploring the utility of extracting these repetitive patterns to build a novel abstraction for diagnosis distributed applications called Workflow Motif. Workflow Motifs describes the frequent processing patterns in the workflow of how requests are processed along with their performance characteristics. These workflow patterns are essentially the building blocks of distributed applications runtime behavior. Different permutation of these workflow motifs will largely make up how requests are processed. Example of frequent patterns may include the work done in consensus protocols or the work done for three-way replication in storage systems. And how workflow motifs help diagnosis is by hiding the complexity during diagnosis by allowing distributed systems to be understood in terms of their building blocks instead of in terms of very specific and detailed behavior. I want to explain the features of workflow motif with an example. Here is a simplified write request in a distributed storage system, and this workflow consists of the work done in both client side and the storage node. Workflow motifs are frequent processing patterns across and within different requests. So, for example, in this graph, motif 1 represents the work done for reading metadata from metadata server, and the motif 2 represents the work done for three-way replication write. Also, workflow motifs are hierarchical and composable, means that a large motif can be composed of smaller motifs. This allows larger motifs to hide complexity of smaller motifs. For example, here motif 3 shows the behavior for writing the data to the backend, which consists of both motif 1 and motif 2 and some other works. The workflow motifs also consist of performance characteristics. This means that for each workflow motif, we keep the mean 95 percentile, 75 percentile, and so on. This allows us to identify the performance behaviors and anomalies. The key enabler for building workflow motif is end-to-end tracing or workflow-centric tracing. And here is the basic explanation of how workflow-centric tracing works. This figure shows the deployment of a distributed storage that keeps the data, a table store that manages the data representation, an application client that reads the data or writes the data. And to capture the request workflow, workflow-centric infrastructure use trace points, which are embedded within the service code base. Trace points are just like logging points, and they can be added manually, or they can be instrumented into the libraries that we are using, or even they can be added during the runtime. Example of low-level, and they also can capture the low-level behaviors. An example of low-level behaviors is, for example, CPU utilization, or the queue length, or, for example, or the state of the node. So when a user starts execution, the tracing infrastructure propagates the contents across the request, such as, for example, request ID or span ID, and then it stitches together the request together to build the workflow. The output of the end-to-end tracing system is either a graph representation of how the system works, or the span-based hierarchical representation of the system works. But in both cases, extracting information from these complex traces is so hard. Our approach to build a workflow motif is to exploit frequent subgraph mining algorithm. And these algorithms help us to find similar patterns within and across traces that we have. They also count for the number of occurrences in the system. So these algorithms are widely used in the world of biology for finding, for example, DNA matching, or they are using in chemistry community for detecting similar components. And we are using frequent subgraph mining to find common patterns that we are finding in the execution traces. And as you can see in this figure, this is again the a part of the write request workflow. And as you can see, this is the pattern for writing, this is the pipeline pattern for writing the three-way replication of data. And each part shows the write request to a disk. However, these algorithms are expensive, and we think that by applying some constraints and some domain knowledge, we can make them simpler and make them applicable to the diagnosis tasks. So now with an example, let's look how a workflow motif can help us to improve the debugging experience. Back to our previous example, the performance team engineer wants to explore how the system works and what is the performance of the scan from a table. So he expects his command to be processed in 10 seconds. However, after reading the data, he figured out that, okay, it takes 50 seconds instead of 10 seconds. So he decides to enable instrumentation, and then he collects traces. So after that, he runs a workflow motif, and the workflow motif finds these frequent patterns within the traces. So he observed that the table store divides his request into smaller reads, and then read them sequentially instead of read them in parallel. So he observed that if these reads were issued in parallel, he could get a better performance, and he identified this as an optimization point and send his observation to the developer team for optimization or performance improvement. And here is the software components and operation for our workflow motif framework, and its goal is to run alongside the distributed application and mine motifs from the traces of request workflow and make these motifs available to diagnosis tools and engineers. We use this framework to measure the effectiveness of using motifs to quickly diagnose the problem in a running system. The workflow-centric, in this picture or figure, the workflow-centric tracing captures the workflow of how system works and the traces for us, and then they are stored in a trace database. The workflow motifs reads traces from the trace database and builds the workflow motifs from them. And then we can query those motifs, or we can annotate the traces for the most common behavior. And finally, we can use them for a wide range of diagnosis tasks. To make these key enablers applicable to our problem, so we first identify the formal definition of what a workflow motif is, and then we define how we can meet our requirements if we want to use this tool. Here is the formal definition of a subgraph, but in general, a frequent subgraph is a frequent patterns or frequent graphs that happens for a certain amount of time in a set of graphs, or between or across a set of graphs. And here, we build on the standard definition of a frequent subgraph in order to fully define a workflow motif. We start from a workflow-centric tracing trace T, and then which is a weighted acyclic graph. And each vertices in the trace represent a trace point, like a function or a span or a library call or an RPC. And edge represents the happens before relationship between these trace points. The edge weights indicates the latencies between successive trace points, and a single layer trace S is a trace created by slicing that trace T into smaller parts. And so, given a set of single-layer traces, the number of times that a processing pattern P occurs within all the traces is called sigma. And if the sigma is larger than a threshold, we identify that as a frequent. But unlike the frequent pattern mining algorithm, here for identifying a pattern to be frequent, we don't need to match the edge weights. Then we define workflow motif as a processing pattern that occurs over certain number of times in the traces, and plus its distribution, and also the distribution of each edge. Our definition of workflow motif is similar to frequent pattern mining's, frequent subgraph in frequent pattern mining tools, and it accounts for edge direction and frequency within and across graphs, and it additionally includes performance characteristics. Our definition satisfies the definition of the abstraction, which means that it allows us to hide the complexity and allows us to understand the complexity in terms of simpler building blocks instead of detailed knowledge. And now I want to discuss the requirements we have from the workflow motif to build the workflow motifs. So some of the frequent processing motifs that we have observed in the traces may execute the same work but in different order. Such frequent processing patterns should be identified as separate motif, not as the same motif. For example, in this figure shows different execution order of a read request and a write request in Ceph Rados Gateway, which is a distributed storage system. And this could happen for several reasons. For example, the first reason could be correct execution in lower stack, and then the engineers can use it for understanding the system behavior. The second one could be just an implementation bug. Instead of writing function A and function B, we just have function B and function A. which have to be identified. And the other one is that it may cause a performance bug, which means that one direction latency is different than the other direction latency. So the workflow motif should be able to identify this behavior and should be able to capture this behavior. The second requirement is that we need to find workflow motifs that are within the traces and across traces. For example, there may be some patterns that happens across many, many traces, but does not happen within a single trace. And also there are some workflow motifs that could happen within a single trace for multiple times. For example, they read 4 meg blocks. I discussed for that example. And then it doesn't happen across many traces. So workflow motifs should be able to identify both patterns that happens within traces and across traces. And the third requirement is that workflow motif should show the performance characteristics. So for the performance characteristics, we need to show the distribution of the overall execution time of a workflow motif. We would like to show the latency of the critical path, and we would like to show the distribution of more detailed, for example, the distribution of edges or the distribution of several passes if we have a multi-threaded motif. Now I want to discuss the frequent subgraph mining tools that we are exploring for building the workflow motif tool. One of the first tools is FSG, which is frequent subgraph mining tool. It is a join-based model, which means that it starts with the very smallest subgraphs, and then it tries to add edges and build frequent subgraphs one by one. So unfortunately, this tool is not scalable. It also does not have the edge direction, and moreover, it doesn't look for the traces within the graph. It also looks for the motifs or frequent patterns across graphs. Although it's not the tool that we like to use because it doesn't follow our requirement, this is the very basic tools that all other tools are kind of based on this one. The second tool that we observed was Gaston. Again, unfortunately, it only runs on a single machine. It does not run on a distributed system, and so it is not scalable. It does not follow the edge order, and also it only looks for frequent patterns across traces. But this has a very interesting behavior. The algorithm has a very interesting behavior. It first looks for frequent passes, and then it looks for frequent trees, and then it looks for frequent graphs. So it allows it to find first less complicated patterns and then build on a more complicated patterns. And interestingly, this is the behavior that adapts very well to the nature of workflow traces we observed from HDFS and Ceph. The third tool that we looked was Grammy, and it is it takes a constraint satisfaction approach, which means that it finds a set of minimal appearances that are frequent, and then it doesn't go beyond that. This tool supports the edge order, and it also supports the cross and within graphs mining. However, it does not scale because it runs only on a single machine. We also look at Arabesque, which is a distributed graph mining framework, and it follows the pattern growth like FSG. It follows a pattern growth solution, and it allows for finding frequent patterns within and across graphs. However, it does not support edge direction, and but it is an open source, and we can combine these approach with other approaches to build a satisfy our requirement. And the last approach is ASAP, which is the newest one, and it allows for sampling for finding frequent patterns. And but it's not open source, unfortunately, and we cannot compare it with other approaches, and we cannot explore it more. So our approach is to build on building on these existing frequent patterns. We want to use Arabesque, which provides distributed graph mining for us. We want to use Grammy to provide cross-trace and within-trace within trace patterns, and also allows us to meet our edge direction requirement. We want to use Gaston to be able to start from less complicated patterns and then make more complicated ones. And then we want to use we want to adapt the ASAP approach to be able to support sampling for less overhead. Here is a preliminary results of the some of the patterns we could find in HDFS traces. We captured some workflows from HDFS, and then we run Gaston, one of the tools, on these traces. The right one shows how a read block motifs look like, and the left one shows the read from network motif. We think that this workflow motif is really a powerful tool, and we want to look at some of the use cases. One of the use cases could be compare and contrast traces. For example, we can run workflow motif on the traces, find the frequent patterns, and then chop each trace into its frequent patterns, and then compare those frequent patterns together to, for example, find the performance anomalies or to find the structural anomalies. The other one is system optimization, that, for example, we can find motifs that are at the tail latency of execution and then report those for optimization. The other use case could be finding structural anomalies during execution by finding the most frequent ones and then filter those and then find the less frequent ones, which means that there was an anomaly in the system. In summary, we find that powerful abstraction helps engineers to build distributed systems, but the de facto approach for debugging them is using less sophisticated abstractions. We introduced workflow motif, which is a novel abstraction for debugging distributed systems, and a workflow motif is a frequent processing pattern that could be extracted from the workflow traces. And our tool to do that is using a workflow tracing tool as a key enabler. And we use frequent pattern mining tools to extract the workflow motifs. And we think that combination of Arabesque, Grammy, and Gaston allows us to build very good abstractions. That's it.
Wow, that was fabulous. I imagine there's questions, but first I have a question. Is it possible to play with this? Can we play with it?
In near future.
Near future,
Yeah.
Okay, near future. Anyone have any other questions? Starting in the back, and then I'll get to you.
That was fantastic. Congrats on the work. So I kind of wanted to know, are you using, what kind of trace format and backend are you using for this work?
So currently we are using traces that are in the form of graphs, and we use X-trace traces, but before using X-trace traces, we played with traces we captured from Jaeger, and then from the traces we captured from Jaeger, we tried to build a graph, execution graph, and run on those. But currently we are using X-trace as our...
Great. I think there's another question. There it is.
Yeah, so I'm kind of new to a lot of this. Could you help me understand what so for instance, the span IDs in the open tracing framework and that level of, say, with microservices, so to kind of ground this or make this more concrete, can you help explain what the overlap between these, the workflow motifs are between just a simple span ID trace? Is it operating at a higher level of abstraction or granularity, or is it at about the same? Can you kind of explain where it sets?
So the span model, it shows you the workflow that happens within a single trace. But we want to be able to extract patterns that are happening across many, many traces, not only a single trace.
So higher level casual associations of
Yeah.
these as a larger grained workflow.
But not only, for example, because the span model is also hierarchical, it could consist of a very small portion of like just a function to the very, very large one, like the parent, the root trace is just the overall write request, for example, which consists of maybe 1,000 or even more than that. So our model is to build from the very small one, find the patterns that are very fine granular to the patterns that are very coarse granular. So we are not only limited to the higher level.
Gotcha. So you would start with the open tracing style span ID pieces, yeah. And then without having to add in manual constructs for the larger workflow pieces, you would be able to extract those and pull those out and find performance metrics or other concerns around it in debugging.
Yeah, that's our approach. Yeah.
Thank you.
Sure.
Okay, I think we're at about time. So let's see another round of applause for Mania here.